Hello everyone, this is Sumit Kumar and today I am going to tell you something about group theory. And one of the important part in group theory is to find number of elements of order 2 in a finite group. So suppose if I say does there exist a finite group G such that number of elements of order 2 in G is 60. So can you find that group, that finite group? And even more, if I say find a group, find a finite abelian group of group G such that number of elements of order 2 is 60, let's say 30, whatever. So how to answer those questions? You know, when someone will ask to find a finite abelian groups of certain properties, and not finite, not finite abelian group, just a finite abelian groups. If someone will ask find a finite group with this property of related to elements order. So how one can answer those questions? So it's really important in group theory. So how to answer those questions? So recall there are some theorems related to finite abelian groups, and there is some theorems to like how a finite abelian group is look like. You know, that theorem is called structure theorem, that if you give me a finite abelian group of order, let's say 10, then these are the choices for GB. Or if you are going to give me a finite abelian group of order 20, then these are the chances for a finite abelian group of order 20s look like this kind of groups. Matlab, that group is isomorphic to this kind of groups. So these are called structure theorems for finite abelian groups. And but in general, to find abelian groups of finite or infinite with certain kinds of properties related to elements order, it's not an easy job. So how to solve those problems? So today I am going to do that. Just I will take elements of order 2, and because I feel this is somehow important in if you are going to write exams called IIT JAM, NET, GATE, NBHM, anything. So here is the question. This question asked in this TFR 2017, and the question is here: there exists a finite abelian group G containing exactly 60 elements of order 2. So they are asking, is this statement true or false, whatever. So this is the statement. So there exists a finite abelian group G containing exactly 60 elements of order 2. So this statement is true or false. That's why. If it is true, give that group. If false, prove it. Right? So how one can answer this question? So today I am going to do more general. Not I will consider as abelian group. My question is, can you find finite group with this property? Can you find a finite group such that number of elements of order 2 is exactly 60? Does there exist? If no, prove it. If yes, give that example. So I am going to do more general. If you have let's say finite group of order 60, finite group of order let's say 100, 2000, anything, then how I can judge? Look, these are the number of elements of order 2 is like this. Okay? So we are going to do that. So there are some theorems I have to recall that. So to answer this question, first let me recall some basic theorems, whatever you know. So recall some theorems. So recall some basic facts. What are those basic facts? That if you are working over a finite abelian group or finite group, if G is a finite group and A belongs to G, A is an element of the group G, then order of A divides order of G. This is one of the theorem. This is actually Lagrange's theorem. Corollaries of Lagrange's theorem. Very important theorem and very important results. So somehow this theorem reduces my burden. You know, if you are saying, can you find a finite group of odd order such that number of elements of order 2 is 60, is not true. Because if there is an element of order 2, then 2 must divide order of G. That means order of G must be even. Right? If you are looking for a group where you have to find number of elements of order 2, you have to look for those groups whose orders is even number, not odd. So from here I can conclude, if there exists A belongs to G such that order of A is 2 and G is finite, then by above theorem 2 must divide order of G. That means, that is, order of G is even. Simple. That means to find a finite group or to looking for a finite group having elements of order 2, you have to just look for those groups whose orders are even number. Right? So you don't have to look for a group of order 27, you don't have to look for a group of order, let's say 101 and blah blah. Okay? So this is enough. Now, and so I have not used so far abelian and all those stuffs. Lagrange's theorem holds for any finite group. So just finite property I have used so far. Good. So now to answer how to find number of elements of order 2. So this is my claim, claim 1. So just I am considering G is a finite group, okay? Because if G is in infinite group, it is not possible to answer this kind of questions, you know. It's not possible. I mean possible, but you don't know how to answer those questions. If group is like infinite order group like Z, R, then there is no element of order 2 with respect to addition and all those things. So you have to give the precise group. So just I am looking for finite group. To answer infinite group, still one can answer, but right now I am not interested in those questions. Just I am concentrating, focusing only on finite groups. Okay? So let's answer. So if G is a finite group, then number of elements of order 2 is odd. This is my claim. This is my claim. If you are working over a finite group, doesn't matter that group is abelian, non-abelian, cyclic, blah blah. I am not interested in that. If you are asking me for number of elements of order 2, I will say it is odd. Odd. Always. How to prove this claim? How one can approach this question? It's very important, very basic, so elementary that one should know. If you are studying group theory, if you are studying some examples of finite groups, you should know. How to prove? So proof of my claim. Proof of claim. 1. How to prove this claim? So if I say what you have given me, so you said G is finite. G is finite, right? So there will be two choices. Order of G is either even and order of G is either odd. Right? These are the two choices for a finite group. Either it is even or either odd or even. So odd case it is not possible, because I told you if there exists an element of order 2, then that 2 must divide order of G by Lagrange's theorem. So this case is not possible. If you are looking for an elements of order 2, so this case is not possible. So to looking for an elements of order 2, G must be of even order. First case is this. That's what I have written here. Okay. Now here in this case, if somehow, see, in this group there are two choices. There is an element A called identity element, and there are some elements which are non-identity, right? In each group there is a unique identity element and non-identity elements. So here the order of this element is always 1. Order of an identity element is always 1. And what about non-identity elements? In non-identity elements, there are elements, there may be elements of order 2, there will be some elements of order 2, and there will be some elements of having element not order 2. These are diagrams, you know. If you choose any elements from A belongs to G, there are two choices. A will be identity or A will be not identity. If A is identity, then order of that element is 1. If it is not identity, then order of A either be 2 or not equal to. These are the two chances. Fine. Good. If I prove it that number of elements of having order not equal to 2 is what should I say? Is, let's see how many elements of this kind. Let me do that first. If I say these are even, then we are done. If this is even number of elements, means number of elements in a group having order at least 3. If I say that those elements are in even numbers, then these are even numbers plus 1 odd numbers. If you subtract an odd number in an even number, what you will get? An odd number. So number of elements of order 2 in a group of even order is always odd. That's what we have to do. So just try to prove that number of elements in a group having order at least 2, at least 3, means either 3 or greater than equal to 3 is odd. Let me prove this. So for this, to prove this claim, recall one again basic fact that order of A is always order of A inverse. So simple, so elementary. If order of A is suppose 10, then order of A inverse is also 10. Just prove it. Go through the definition of an order. What do you mean by order of an element? Go through it, compute it. Okay? So simple. Next. Next, consider this set. Consider this set containing x inverse such that order of x is greater than equal to 3. Consider this set. Look at this set very carefully. Who I have chosen? I am just asking here what properties you have. Tell me. Okay, they are saying if A is an element of some order, then A inverse of A order is exactly the order of A. And my claim here, if order of x is greater than equal to 3, then x is not equal to x inverse. Why so? Otherwise means if x equal to x inverse implies x square equal to identity. That implies order of x is less than equal to 2, which is a contradiction, because I am assuming order of x is at least 3. On that case, x is never going to be x inverse. X inverse may be something else, but it is not going to be x. Okay? Because if it is, then order of x is at most 2. That's a false. I am assuming order of x is at least 3. Okay? So this and these are distinct elements. So this is a pair with distinct elements. Okay? So because if you have a group, if x belongs to G, then x inverse is also belongs to G, right? So these two distinct elements in group G, provided order of x is at least 3. So how many such elements are there? So now I am interested in number of elements in A. So this set exactly containing all those elements having order at least 3. So what is the number of elements in A? Can you tell me how many elements? Because G is finite. So this is a subset, this is of course a subset of G. I mean dot x in x inverse means if you say that collection, this is of course you could say subset of G cross G inverse. But I am asking how many elements are there in A such that x belongs to G and x, the order of x is at least 3. So this is always in pair it will come, and how many elements are there in such kind of elements? It is always number of element in A is even. How I am saying? See, if x is there, x inverse is there. So consider this pairs x inverse. So number of elements. So let me write more precisely. Therefore, number of elements having order at least 3 is an even number. That's what I have proved. That's what I have proved. If you are looking for an element of order at least 3 is always an even number. Why? If x is an element of order at least 3, then x inverse element is also order at least 3, and x inverse are not same. So they are coming in pairs. So how many pairs? So each x and x, so 2 elements, 2 plus 2 plus 2. How many times? How many those elements are there? Exactly that. So 2 times something is always even. That's why it is even. Okay? So simple. So now let's come to the order of G. Now order of G is even. Since order of G is even, this is given. Order of G is even number. Identity element has order 1. Identity element has order 1 plus number of elements of order at least 3 is always number of elements of order at least 3 is always even number. So 1 plus even, what is that? Or, and group order is even, so it is like 2 times n. So here what is in the middle? This will be number of elements of order 2. Exactly. Because any element if you pick from group, either its elements order is 1 or 2 or at least 3. These are the 3 choices. So from this and this we are getting odd number. So number of elements of order 2 is equal to 2n minus an odd number. Even number minus odd number. What is that? Odd number. So you see, number of elements of order 2 in a finite group is always odd, provided that group is of even order. Clearly? So that's what exactly we have proved. I have not used any technical term that G is abelian group, cyclic group, blah blah, nothing. Just finite group. You give me finite group, I will say that number of elements of order 2. If that finite group is of odd order, number of elements of order 2 is 0. If that group is even order, number of elements of order 2 in that group is always in odd form. So any odd number, so there will be at least one element of order 2. So this theorem is saying, this claim is saying that number of elements of order 2 in a even group order is always at least 1. There always exists an element of order 2 in a finite group of even order. Okay, because 2 must divide that order. See, because odd number always start with 1. Is that clear? So simple. See, if you have proved something, don't stop here. Go through all its corollaries. Ask to this theorem what hidden information you have. They will say everything. Okay, so go through that. Good. Next. So we have proved, hence the claim. Hence the claim. Okay? Next. So this was like any finite group. But here the question is, so to answer this question, there exists a finite abelian group G containing exactly 60 elements of order 2. From that claim, this is already false statement, right? Because number of elements of order 2 in a finite group, even though I will not look for abelian group also. Finite abelian group means finite group. And you are saying that there exists exactly 60 elements of order 2 is false. Always number of elements of order 2 in a finite group is odd. A 60 is not an odd number. So this statement is false. Fine. But if I say, so this question we have done, okay? So for the TFR purpose, we have already answered this question. But if suppose I ask, there exists a finite abelian group G containing exactly 61 elements of order 2, how one can answer?